In this video, we're going to look at part 1 in a series of predicting reaction types as found in Chapter 9. There are 5 major reaction types in Chapter 9, SN1, SN2, E1, E2, and NGP. Before we watch this video, please make sure you've looked at all of these concepts because I will be talking about them like you know them. First thing we analyze every time is the carbon that has the leaving group. So let's look at that first. The acceptable short form for a carbon with a leaving group is R attached to X, with X being the leaving group. And in our example, and all 3 examples on this page, we have a secondary carbon, which means we do not know whether this is SN1 or SN2. We always look at the SN1, SN2 first. With a secondary carbon attached to a leaving group, here iodine, we do not know whether it's SN1 or SN2. Further analysis will be necessary. Looking down the page, the only thing that has changed is the leaving group, but they're all excellent leaving groups. So the same category for analysis item 1 in all 3 problems. So, to make our conclusion, we're going to have to look further. The nucleophiles are in blue on this page, and this category of S with an anion is a strong nucleophile. Strong nucleophiles favor the bimolecular reaction where the nucleophile is actually involved in the rate-determining step. Strong nucleophiles favor that. In the second one, the nucleophile is a neutral sulfur. Being neutral makes it less reactive towards positive charges. It goes down to the moderate nucleophile category. Moderate category means we do not know whether it's SN1 or SN2 based on the nucleophilic analysis, and we have the same category down here. Third thing in our analysis is always the solvent. We have them in pink on this page. We use the same solvent for the first 2. It's called acetonitrile with a triple bond between the carbon and the nitrogen. That is the Cadillac of SN2 solvents, and I'll put the category down here. So what we have for our first reaction is a polar aprotic solvent, acetonitrile, which favors SN2. I've got 2 things in here saying SN2 and 1 thing saying I don't know. My conclusion is definitely SN2. SN2, which involves a backside attack by my nucleophile on the carbon with the leaving group. A mechanism is not required for this problem, but I'll show it to you here just for fun. Here we're doing a backside attack on a stereocenter that used to be R. In your product, I need to clearly see an S stereocenter because there will be an inversion, and the product will look like this. Here's an obviously S product. On the test, it's hard to visualize it. I hope this gives you a visual. The backside of a dash is definitely a wedge. Everything got pushed over to the right, and the H got pushed back. But I do not expect you to be able to give me this visualization. Here's the easiest way to show an inversion of a stereocenter. Copy your original. Get rid of the leaving group. Make that a wedge. Flip the H to a dash. And put on the rest of the nucleophile. So when doing an SN2 reaction, this is S. Used to be R. I do not need to see the mechanism or you attempting to show a good visual on an SN2. So I don't need to see those things. This is all I need to see right here. I do not need to see the leaving group unless I ask for it, and this would be a complete answer worth 6 points. Next example, The only change I've made is to change the nucleophile from strong to moderate. I've got the same solvent. My decision-making process still leans towards SN2, but not till the very end. It's going to be a much slower SN2 because your nucleophile is far less reactive, being neutral. The product result will be the same. And there you have it. And our conclusion was based solely on pink. And yes, I know I do get carried away with colors occasionally, but bear with me. And the last one, we have indecision, and a new type of solvent. That is a protic solvent. I know it's a protic solvent because it's an alcohol, and alcohols can hydrogen bond, and all solvents that can hydrogen bond are polar protic. Polar protic solvents are good for SN1 reactions. So now we have to explore what happens during an SN1 reaction. I will do the mechanism and erase it because it's not really part of this question. In an SN1 reaction, first step involves only one molecule. That's where the 1 comes from in the name. And you're generating a carbocation. The rate determining step in an SN1 reaction, SN1, is to form a carbocation. Carbocations are flat. It means the nucleophile is going to approach 50% from the top and 50% from the bottom, giving us these two molecules. We have this sulfonium here and this sulfonium here, 50-50. One came from behind, generating a bond that's a dash, and the other came from in front, generating a bond that's a wedge. The solvent will neutralize these strong acids, and I hope I need not remind you that a sulfonium would be even more or a stronger acid than an oxonium, which is a negative pKa. Sulfoniums are even a little stronger, and they will be neutralized. I don't want to see sulfoniums in your product prediction. I don't even want to see you draw two products. Here's what I want to see. Do not make your life hard. We're neutralizing sulfur. You're going to get a 50-50 mix of two enantiomers. Let's just make sure that's a normal bond. You just have to, don't leave it like this. Don't leave it like this. You got to show me, that's a 50-50 mix of two enantiomers. My box is moving. I'm not that upset. 50-50 mix of R and S on the stereo center right here. And that would be your result. It's a thioether, and you have to show me that there's two of them. I hope you found this video useful. You do not need to show the mechanism, so I'm going to erase it. It was not really part of my answer. It's part of my thought process. I'm going to get rid of the box there. And there you have it. I hope you found this video on analyzing reaction types part 1 to be useful, and there will be another type very soon.